Imagine building a high-performance sports car, but having to manually forge every individual screw, gear, and bolt from scratch, depending on whether the car is driving on asphalt or gravel or dirt.
Oh man, that sounds incredibly exhausting.
Right. Every new environment demands a complete, from the ground-up reconstruction of the underlying mechanics. And it sounds wild, but when we look at the world of artificial intelligence today, that is the reality engineers face.
It really is. A deep learning model today can have, billions of parameters executing trillions of math operations every single second.
Yeah, and now imagine having to manually rebuild the structural foundation of those operations every time you want to move the model from a desktop computer to a mobile phone.
It's a massive headache.
So today we are taking a deep dive into a brilliant solution to this nightmare. We are looking at an automated system that figures out how to run complex deep learning models on almost any chip, entirely on its own.
Which is such a huge leap forward.
Spot on. We are diving into a pivotal research paper titled TVM, an automated end-to-end optimizing compiler for deep learning. Our mission for you today is to unpack how this system eliminates the manual labor required to translate high-level AI software into instructions for physical hardware.
Because the friction in that translation process is really the defining bottleneck in modern machine learning deployment right now.
To understand the value of the TVM compiler, we first need to establish why taking a model from a framework like PyTorch or TensorFlow and running it up on a mobile phone or a custom chip is so incredibly difficult today.
Right, so when a researcher builds a model in PyTorch, they are writing in a language designed for human comprehension. They define layers, activation functions, and loss metrics.
They're definitely not writing instructions for allocating memory on a microchip.
No, absolutely not. So to bridge that gap, current frameworks rely on a narrow set of heavily engineered vendor-specific operator libraries.
Like NVIDIA's Cadena and library for server-class GPUs, right?
That is right.
So we have this brilliant software, but it relies on an exclusive club of highly specialized translators to actually do the math.
And you might be thinking, well, why can't we just write one universal translator?
Because hardware is not standardized at all. Think of it like writing a universally acclaimed screenplay in English. To produce the play, you have to manually rewrite it and culturalize it for every single regional dialect in the world.
Which is a huge undertaking.
It is. To do that, you have to rely on a few scarce, highly paid translators. And if your specific dialect does not have a dedicated translator, well, your play just cannot be performed there.
To take that theater analogy a step further, imagine if one theater only speaks in single words while another only understands like group chants.
That is a great way to put it.
That mirrors how wildly hardware targets diverge. A central processing unit, or CPU, a graphics processing unit, the GPU, and a specialized accelerator like a tensor processing unit, they all possess completely different memory organizations.
And they use entirely different compute primitives, too.
Yes. A CPU might optimize for scalar math, processing just one number at a time. A GPU might optimize for vector math, processing arrays of numbers simultaneously.
While a TPU-like accelerator introduces optimized tensor compute primitives operating on massive multidimensional blocks of data all at once.
Furthermore, they handle memory hierarchies so differently. CPUs use implicitly managed caches, while specialized accelerators often require explicit software management of the on-chip memory.
So porting these high-level models to all these new hardware designs requires massive, completely unsustainable manual engineering. Human developers are hand-coding the math for every variation.
Which just does not scale.
No, it does not. If manual translation for every new chip is impossible, how does TVM approach the problem without requiring a human developer in the loop?
Well, TVM takes an end-to-end approach, starting from the very top. It reorganizes the model's structure before it even touches the physical hardware.
Okay, I follow.
The compiler first converts the model into a computational graph. This graph acts as an intermediate representation. It strips away the Python code and leaves only a pure mathematical blueprint.
So in this graph, each node represents a mathematical operation on tensors, and the edges connecting the nodes represent the data flow dependencies between those operations.
Yes, that is correct. Before worrying about the specific silicon, TVM analyzes this global view to find overarching inefficiencies.
And a major feature applied at this stage is called operator fusion. I understand the goal there is to avoid costly trips to memory, but how does the software know what to fuse before it knows the hardware's layout?
To answer that, we should probably unpack the mechanics of a memory trip first.
Let us do it. So you calculate a value, push it down the wire into main RAM, and then the very next operation has to reach all the way back into RAM to pull that specific value out again.
And the latency of that RAM retrieval can be orders of magnitude slower than the calculation itself. Operator fusion prevents the data from ever leaving the processor's localized fast access registers.
It combines multiple operations into a single, seamless kernel.
Which is brilliant. The sources outline how TVM classifies operators into distinct categories to determine their fusion limits based on data dependency.
Let us break down those categories by how they behave. Some operations are simple one-to-one mappings. It is like painting a fence. You can paint board 1, then board 2. You do not need to look at the whole fence at once.
I like that analogy. Those are injective operators, like adding a constant value to every number in a data set. You can easily combine those with other local operations.
Then you have reduction operators, which compress data, like finding the sum of all elements in a tensor.
The complexity increases with complex outfusible operators. Think of a two-dimensional convolution analyzing a grid of pixels to find a pattern.
Oh, sure. You can fuse a simple element-wise map to the output of a convolution because the data flow remains predictable, but the convolution itself requires careful memory management.
And finally, the system identifies opaque operators.
Sorting a massive list of numbers is an opaque operation. If an operation requires looking at the entire data set at once to complete its task, you have to stop, save the memory, and sort it.
Right. You cannot just fuse that on the fly because the next step depends on the final sorted order of every single item.
So by applying generic rules to combine these categories, like fusing a scale reduction with a sum, TVM yields a 1.2x to 2x speedup just by reducing memory access.
That is a massive gain for doing no extra math.
TVM also applies data layout transformation at this graph level. It converts internal data layouts into forms that are friendly to the target backend.
Because the standard row major or column major storage formats are often highly inefficient for specialized tensor processors.
So if a specific hardware accelerator performs best when data is tiled into 4x4 chunks to optimize for access locality, TVM rearranges the graph to feed the data in that specific format.
Transforming the layout at the graph level ensures the hardware operates at peak utilization without wasting cycles reorganizing data on the fly.
Now, I want to ask a probing question here. Fusing operations together at the graph level sounds efficient, but does fusing everything together risk creating one giant, inflexible clump of code?
How do you mean?
Well, if we fuse a dozen unique patterns together, we suddenly need a specific hardware kernel for that bizarre 12-step combination.
That limitation is actually the downfall of traditional frameworks. If a traditional framework fuses operations, it still relies on the underlying vendor library having a pre-written implementation for that specific fused pattern.
Yes, they probably do not have.
Right. As new operators emerge, the number of possible fused combinations explodes combinatorially. Hand-tuning a convolution for a standard CPU is difficult enough.
Hand-tuning a fused kernel that combines a convolution, a reduction, and a specific data layout transformation is a combinatorial nightmare.
It really is, and this forces a transition from top-down graph optimization to bottom-up operator-level code generation. TVM must generate the actual machine instructions dynamically.
To handle the actual machine instructions without predefined libraries, TVM introduces a tensor expression language. This language separates the computing rule, the math itself, from the schedule.
The schedule explicitly dictates which loops to run, which memory bytes to allocate, and which threads to deploy.
Going back to our analogies, this is like separating the recipe from the kitchen equipment.
Oh, that is a good one.
You have the mathematical recipe for baking the cake, but the schedule allows you to bake that same cake perfectly, whether you were using a microwave, a campfire, or a professional convection oven.
So the math stays the same, only the execution schedule changes to fit the environment.
Decoupling compute and schedule is an extension of principles found in earlier languages like Halid, right?
Yes. And TVM extends this to support specialized deep learning accelerators through a process called tensorization.
Because hardware vendors frequently introduce custom tensor compute primitives into new chips.
Exactly. I mean, that is true. These are specialized physical instructions built directly into the silicon to perform massive matrix multiplications instantly.
And tensorization separates these target hardware intrinsics from the schedule.
So when a vendor releases a new chip, they provide the specific instructions required to trigger their custom matrix multipliers.
Tensorization then provides an extensible mechanism where a developer can declare the behavior of this new hardware intrinsic using the tensor expression language.
And TVM's compiler then seamlessly integrates it into the generated code, mapping the abstract math of the neural network directly onto the physical layout of the new chip.
TVM also has to tackle explicit memory latency hiding. Hiding the delay of fetching data from main memory is a massive hurdle.
It is a huge bottleneck.
Let us visualize this. The processor is a hyperactive chef, and the main memory is a refrigerator down the hall.
Okay, I am picturing it.
If the chef has to wait for ingredients to arrive from the fridge, the kitchen stops working. On standard CPUs, hardware multi-threading hides this latency. The processor simply switches to another thread, another recipe, while waiting for the first set of ingredients to arrive.
But specialized TPU-like accelerators operate differently. They use a decoupled access execute architecture, or DAE for short.
And these chips remove the complex multi-threading hardware to save space for more raw math calculators, right?
Yes, they offload the complexity of scheduling memory fetches entirely to the software.
Wow. So if the software does not explicitly tell the hardware to fetch the next batch of data while it is currently computing the current batch, the entire chip stalls.
It does. Programming for a DAE architecture is incredibly complex because it requires explicit, fine-grained synchronization.
The sources mention the programmer manually inserting low-level dependence tokens. It sounds like micromanaging the silicon, ensuring it reads a value before writing over it.
It is?
It is like telling the chef to explicitly check that the bowl is empty before cracking an egg into it.
TVM introduces a virtual threading scheduling primitive to solve this. Virtual threading essentially tricks the hardware.
Tricks at how?
Well, the programmer specifies a high-level data parallel program, assuming standard hardware multi-threading is available. TVM automatically lowers this virtual thread parallel program into a single, highly orchestrated instruction stream.
Oh, I see. It injects the necessary explicit synchronization operations, the read after write and write after read dependencies.
By faking the presence of multiple threads, the compiler automatically sneaks the memory fetch commands into the tiny microseconds where the processor would normally be waiting idly.
Which guarantees the DAE hardware pipeline remains full. That is incredibly clever.
It really is.
So a compiler must decide whether to unroll a loop, how large to tile a memory block, and which virtual thread schedule to use. We have all these scheduling primitives, loop tiling options, data layouts, and virtual threading capabilities.
And the number of possible ways to run a single piece of code explodes into the billions.
If the system were to rely on standard black box auto-tuning, it would compile and run every single configuration on the hardware to measure the fastest one.
Which would take forever. Evaluating a single schedule on physical hardware might take seconds. Multiplying that by billions of possible configurations results in compilation times stretching into decades for a single model.
So black box auto-tuning is completely unsustainable for the combinatorial explosion of modern deep learning deployments.
Instead of guessing forever, TVM uses a machine learning-based cost model as the brain of the compiler.
The ML cost model predicts the performance of a given schedule configuration without having to compile and run it every time.
There is a strong irony here, do you not think?
Oh, absolutely. We are looking at a system that uses a machine learning model to figure out the optimal way to compile and run machine learning code. It is an algorithmic snake eating its own tail.
Human engineers became so exhausted writing compilers for artificial intelligence that they trained an artificial intelligence to do the compiling for them.
But the machine learning model needs data to make its predictions. What specific features is the algorithm extracting from the code to determine if it will run fast or slow?
The model relies on gradient tree boosting, specifically an algorithm called XGBoost. It extracts features directly from the abstract syntax tree of the loop program.
So the model looks at the memory access count of each buffer at each loop level, assessing how often data is reused.
It calculates the memory footprint to ensure it fits within the hardware's specific cache size.
It also analyzes loop annotations, identifying whether a loop is unrolled into a flat sequence of instructions or vectorized to process multiple data points simultaneously.
Right, and by evaluating these features mathematically, the model outputs a predicted execution time.
The researchers also tested a neural network model called TreeRAN-N.
Right, they did. TreeRAN-N showed similar predictive quality without requiring manual feature engineering. However, compiling thousands of models requires speed. XGBoost was ultimately selected as the default because it trains significantly faster,
allowing the compiler to iterate more rapidly. I have to push back on the cost model's capabilities for a moment. How does this ML cost model avoid making terrible predictions when it encounters a brand new piece of hardware it has never seen before?
That is a fair concern.
Because if the model was trained on the memory hierarchy of a server GPU, its predictions for the tiny cache of a mobile phone chip would be completely useless.
TVM accounts for unseen hardware through continuous data collection. The system utilizes a custom remote procedure call-based distributed device pool.
Oh, wow. This RPC infrastructure connects a fleet of physical devices, like smartphones, embedded CPUs, and FPGA boards, directly to the central compiler database.
So the system is constantly running micro-experiments on real hardware.
It compiles a small piece of code, sends it across the network to a physical phone or an FPGA board sitting on a server rack somewhere, and measures the execution time down to the millisecond.
The Schedule Explorer navigates the massive configuration search space using the ML cost model as a guide. When it identifies a promising schedule, it sends the compiled code via RPC to execute on the actual target hardware.
The real-world execution time is measured, recorded, and fed back into the XGBoost model as new training data.
The cost model continuously improves its predictive accuracy specifically for the hardware it is currently targeting.
It maps out the optimal execution path dynamically, entirely bypassing the need for a human engineer to guess the best configuration.
Which is a game changer.
An elegant theoretical model is fascinating, but, I imagine NVIDIA's custom libraries are almost impossible to beat. How did TVM perform in the real world when tested against the handcrafted code built by the hardware vendors themselves?
The results are pretty staggering. The paper outlines performance tests across 4 distinct platforms. On a server-class GPU, the NVIDIA Titan X, TVM achieves speedups ranging from 1.6x to 3.8x over existing frameworks like TensorFlow and MXNet.
And those frameworks rely on the highly optimized cuDNN library, which represents thousands of hours of manual engineering by NVIDIA developers.
The massive 3.8x speedup is really the most telling statistic there.
That happened on a DQ network workload, right? Because the DQN used unconventional 4x4 convolutions.
That is right. Standard vendor libraries are aggressively optimized for common configurations like 3x3 matrices, but they stumble on edge cases.
TVM's automated process optimized the 4x4 convolution perfectly because it did not rely on pre-written assumptions. It simply calculated the optimal mathematical path.
Moving to an embedded CPU environment, an ARM Cortex A53, TVM actually outperformed hand-optimized TensorFlow Lite.
It demonstrated the ability to generate highly optimized code for ultra-low precision inference. This involves utilizing 2-bit activations and 1-bit weights.
And this level of quantization requires packing data into wider standard types and replacing standard multiplication with complex bitwise reduction operations.
TVM generated code that outpaced handcrafted low-precision libraries simply because it could adapt to precision configurations that the vendor libraries did not support.
The system is actively beating human engineers because humans cannot predict and hand code every single unconventional workload or future hardware design.
This was verified again on the mobile GPU test, using an ARM Mali processor, achieving 1.2x to 1.6x speedups, right?
Yes. And finally, they tested an FPGA accelerator. They designed a custom, bare-bones piece of hardware called the Vanilla Deep Learning Accelerator.
And TVM successfully targeted this completely custom architecture, reaching a 40x speedup on offloaded convolutions compared to running them on the embedded CPU.
The Vanilla Deep Learning Accelerator evaluation proves the system can adapt to brand new hardware intrinsics on the fly.
Because an FPGA is a field-programmable gate array, meaning the physical circuits can be reconfigured after manufacturing.
By deploying a custom deep learning design on an FPGA, the researchers presented TVM with a completely foreign environment.
Yet TVM still analyzed the hardware instructions and mapped out an execution strategy that yielded a massive performance multiplier.
It removes the necessity of waiting for hardware vendors to release updated libraries every time a researcher invents a new neural network architecture.
So we started by looking at the massive gap between deep learning software and the physical silicon it runs on. TVM bridges that gap through top-down graph optimization like operator fusion, bottom-up tensorization and latency hiding, and an automated ML cost model.
Which is quite the tool set.
Understanding this architecture clarifies for you why performance portability has historically been so difficult to achieve, and how automated compilers provide the technical solution to bypass vendor-locked libraries entirely.
And the technical architecture presents a final provocative thought for you to consider.
Oh, let us hear it.
A compiler like TVM uses machine learning to continually map the optimal execution path for any given chip. The mathematical relationship between the software and the silicon is entirely quantifiable.
Okay, I'm following.
It is technically plausible that this same machine learning cost model could eventually be run in reverse to automatically design the perfect hardware architecture for a specific neural network.